do y'all know what a record is? It's pre-CDs, it's pre-cassettes, and it is a rotating disc, okay? But instead of being read with a laser, it's read with a little needle, okay? And so a record is placed on a turntable, initially at rest. Now that's a common phrasing, but now, I mean, is linear velocity initial still 0? Yes. But now think in angular terms, what else could represent or be 0? At rest, do we have any rotation? No rotation. So initial angular velocity, 0. And maybe on this record, you put white out or you paint one little edge of it, just one dot. I mentioned earlier about my shoulder rotating. You focus on one spot, okay? If you do so, then your initial angular position is 0. When the table is turned on, so there's a motor that's going to lead to the rotation, the record uniformly accelerates. Does this mean cruise control? It's going to rotate at a constant angular velocity? No, it's constantly changing its angular velocity. And so remember, uniformly accelerates, that's a constant alpha, not omega. And it says to a max speed of 60 revolutions per second after only half a second. Wait, revolutions per second? Revolutions? I thought you said the SI unit for angular velocity was radians per second, which is actually true. Part A, what is the final angular velocity of the record? And really here we're going for SI units. Y'all, it's just a conversion. I know y'all love dimensional analysis, right? So we know 60 revolutions per second, but I want to get rid of revolutions and get radians. Well, revolutions is just another way of saying a circle. So one circle has how many radians? 2 pi. And so revolutions goes away. Now I'm just, for simplicity, I'm going to keep it in terms of pi. And so 120 pi radians per second is the final angular velocity. Good. What is the record's angular acceleration, alpha? Well, the defining equation is a change in angular velocity divided by a change in time. Delta, final minus initial. And they told us it starts from rest. That includes angular velocity starts at 0. And then the time, I'm just going to look at time initial is 0, however, that one hopefully you're used to being flexible with. And so it goes 120 pi, keep your pi, and the time that it's taken to get to this velocity is going to be 0.5 seconds. So 120 divided by 1/2 to 240 pi, keep your pi, and then the unit for angular acceleration, radians per second squared. And that's alpha, and that's constant, they said, okay? C, how many revolutions does the record make in this half a second? Let me finish this one, okay? How many revolutions? Well, we know 1 revolution is 2 pi radians, okay? And we know the acceleration, radians per second squared. We need to know the total angular displacement in 0.5 seconds. Moral of the story, we're going to use one of our new constant angular acceleration equations to solve for delta theta, our angular displacement. And so which one are we going to use? Well, we know alpha is 240. We know the time is 0.5 seconds. We know it initially starts at rest. And actually now we do know the final So there's a couple equations we can use. Do y'all have a suggestion? The second one, I'm assuming you meant this one. Okay. So bear with me here. And so this omega t cancels out, and we're left with 1/2 times 240 pi times 0.5 squared. So putting that in terms of pi, we get what? Let's see, 120 times 0.25, 1/4 of 120, 1/4 of 120, 30, pi. Keep the pi, okay? And so yes, you can multiply by actual 3.14, or just keep it in terms. Now careful, this isn't our final answer, bear with me. This is how many radians it makes in 0.5 seconds. How do we go to revolutions? Right, divide by the 2 pi. So we have that displacement. 1 revolution is 2 pi radians. So notice our pi is going to cancel out, and 30 over 2 is 15 revolutions. Does it feel different? I mean, it is a little different, but it should feel a lot the same to basic kinematics, okay? So next class, we'll spend about 15-20 minutes to finish this page out, and then we'll move on to torque, which has a good variety of examples, all right? See y'all next class.